And lastly, let's look at mapping indexes using EFCore. Simply put, indexes are used to make lookup of data based on one or more columns more efficient. Just like we can use indexes in a book to quickly find a topic inside the book without having to search each page, indexes on database tables are used to quickly locate data without having to search each row in the database. When we create our entities using EFCore code first migrations, EFCore defaults to creating indexes on primary keys and keys that are used in foreign key relationships. We can also use EFCore to configure new indexes on our table, which we shall see in the upcoming demo. So let's take a look at mapping indexes using EFCore. In this demo, we'll look at creating an index for the orders table on the name column. We'll also create a composite index on the customers table based on the full name of the customer, i.e. the combination of the first and the last name columns. We'll do so by configuring these indexes on the respective entities in the onModel creating method. We're now back inside Visual Studio, and we're looking at the configuration of the order entity in the onModel creating method in the CarvedRock database context. Here we can see that a line has been added that configures an index on the name property of the entity by calling the hasIndex method and passing in a lambda expression that returns the name property of the orders entity. When a migration is created based on this, a migration file will be created that adds an index to the orders table in the database. And if we scroll up a bit here, we can see that a composite index is configured for the customer entity based on the first and last name properties. If we now create a migration based on these changes, we get a migration file which looks like this. Here we see that our two indexes are created. First, the index on the name column is created on the orders table, and secondly, the composite index on the first and the last name is created on the customers table. If we now apply this migration to the database, we can head over to the Server Explorer and see that the indexes have been created. If we open the table definition for the orders table, we can see that an index has been added here on the name column. And if we now open the table definition for the customers table, we can see the composite index on the first and the last name columns that we defined. So that was a very quick look at how we can map indexes using the hasIndex method. We saw how an index was applied to the name column in the orders table, and also how to create a composite index on the first and the last name of a customer. This module has been an introduction to mapping database objects. There are a lot of details that were beyond the scope of this module, but hopefully it has shed some light on some of the ways in which we can integrate some of the more important database objects into our database models. Some of them, such as indexes, are fairly straightforward to work with, but others, like stored procedures, views, and especially user-defined functions, require a bit of reverse engineering. And although they might not feel like a completely natural fit to the way that we're used to interacting with EFCore, we're still able to work with these objects and utilize the powerful querying features that they provide us with. I hope you enjoyed this module. In the next one, we'll look at mapping many-to-many relationships. Hi, and welcome to the Mapping Real-World classes in EFCore 6 course. My name is Torben Jensen, and in this module we'll explore the many-to-many relationship and which options exist for mapping this kind of relationship. To sum it up, a many-to-many relationship is a type of database relationship which associates multiple records in one table with multiple records in another. As you may remember from previous modules, we've already touched upon this type of relationship, and we've also seen it implemented in the form of the relationship that exists between items and orders in the CarvedRock data model. As you may also remember, the design that we currently have is somewhat clumsy when it comes to modeling an order that contains several instances of the same item. In this module, we'll look at how we can overcome that deficiency, and along the way we shall look at various ways of implementing the many-to-many relationship. We'll start by looking at our current implementation, which is implemented as a direct many-to-many relationship with skip navigations. We will then augment this implementation by adding a payload to the join table by introducing a join entity. And then we'll look at how we can model the relationship as an indirect relationship in EFCore by using the join entity that we just created as an intermediary between the two entities. The first thing that we'll be looking at is our existing implementation of a many-to-many relationship, which is the relationship that exists between items and orders in the CarvedRock data model. As we've already discussed, this is implemented as a direct many-to-many relationship. Direct many-to-many relationships are the simplest to set up, and depending on how we need to use them, they offer some advantages, primarily that they're also very easy to use. In order to set them up, we must simply define the relevant collections on our entities and rely on EF Core to do all the hard work of setting up the join entity, which serves as a link between the two entities and which is ultimately mapped to the join table in the database. In the case of the relationship between the items and the orders in the CardRock database, these two entities are joined using the item order join table. And we don't even have to do any special mapping for this to work. EF Core will work out all the SQL that is needed to map the relationship to the database for us, and all we have to do is to define the relationship in our code, and EF Core will then create it on the database. Using the direct approach to map our many-to-many relationship lets us create an implementation that makes a lot of sense from an object-oriented point of view. In a C# class, we wouldn't need a join entity to create a relationship between two entities. So by creating a direct relationship, where for example the collection of items in an order is accessed directly on the order entity, we completely skip having an intermediary entity to link the two parts of our relationship. The fact that we skip the join entity is why such navigation properties are called skip navigations when they're used in relation to many relationships. But in our database we do need such a join entity, or rather we need a join table, for example as mentioned the item order table. This is because most relational databases are not able to create a direct many-to-many relationship, and they're instead implemented using a join table. Creating an implementation that uses skip navigations is especially useful for simple joins where no additional information must be stored along with the join. But as we've already discussed, this is not always the case. For example, in our case, where it would be helpful to be able to add a quantity column to the join table that we could use to indicate how many items were ordered, and possibly some audit information about when the item was added to the order, and so on. This is not supported by the default setup of the direct many-to-many relationship that we have implemented, but in the upcoming demos we shall take a look at how to deal with this. So before we get started with the demo, let's just quickly discuss how the current implementation we have works behind the scenes. So the implementation that we have right now is called a skip navigation without payload. And as you may remember, EF Core implements such skip navigations for us by using property bag entities, which are a special type of entity which only contains indexer properties. These entities are used by EF Core to create the join entity which is mapped to the join table needed to implement the many-to-many relationship on the database. For most purposes, this is an implementation detail which is entirely invisible to us and not something that we would need to interact with. But as we shall soon see, it is actually possible for us to interact with this hidden entity if the need should arise.